David Cote. I'm Chief Data Scientist for Blue Planet Division at Ciena. And today, for this event about reinforcement learning, I want to talk about superhuman networking operations. And yeah, I want to highlight also and give big kudos to my collaborators from Ottawa University. So Professor Shervin Hamadi, as well as the two great students, Sadi and Basel Al-Tamimi. So we worked to, vast majority of what I'll present today, we worked on that together. All right, so yeah, this is what I'll talk about. So, you know, just some introduction. What is Ciena? What's the, you know, just some what is what in telecommunication networks? Because, you know, I'm sure you're not all in this business. And then I'll provide more details about what we did with Ottawa U. So this nice prototype that's running in a real network, but in the lab. So it's not production network just yet. And yeah, we have this prototype that we call Action Recommendation Engine. We have two flavors of it, one based on supervised machine learning, but another one based on reinforcement learning that is actually giving pretty exciting results. And yeah, then every single time I present RL for production telecom networks, there is always a question about, yes, but how will you train your RL for production? How will you deploy in production without crashing the network? And so I'm gonna talk about that as the last topic. So first of all, with the intro, the first piece of intro is about Ciena. Ciena is actually very famous in our industry, but not necessarily well known with the public. So Ciena is a multinational corporation based in the US, and we're building networking systems. So we're basically a vendor for the backbone of the global internet. So we're selling optical networking hardware, but also more and more we're selling software and we're selling professional services. And yeah, we have all these great customers around the world as written on the slide. Yeah, our vision for network end states, this is not my slide, is the standard Ciena corporate slide, but I actually like it a lot and it does fit with the reinforcement learning framework. So you see here this closed loop, and we call it the adaptive network. So at the bottom is when you think of a telecom network, right, you think about antennas and routers and switches and things like that. So this is this hardware programmable infrastructure. So nowadays, not only you can carry huge lot of bits around the world, you know, very large bandwidth, very fast and low latency connectivity, but also one nice thing about the modern networking equipment is they have these APIs and you can control them remotely. And to control the network remotely, we have a whole suite of powerful software. You can use it to control your network remotely, but also to automate all sorts of things. In addition to that, we have this other direction here, the telemetry. So our equipment, and in general in the modern networks, there is a whole lot of telemetry data that is being produced. And here, maybe for this crowd, I will say, obviously, we can use analytics and AI technologies to consume this telemetry data, analyze it, and maybe make sense of it, classify the patterns, report the anomalies, and basically understand automatically, here again, what's going on in the network. Are there issues? Are there hotspots? Is it optimal or not? So that is, but so far I'm talking about kind of a passive read-only operation, the analytics and the AI observing the network with telemetry, but not yet touching it. And I said 2 minutes ago that we also have this software that can touch and provision things on the network. So then there is this missing link here. And you have the AI actually take control of the software. So today, this is not the case. For production networks, this is done here by humans. But for talk about reinforcement learning, right, you can see how if you do close this loop, and we do it in our labs, and we more and more so in production actually for maybe simpler closed loop at first, feedback loops, you can think. And then, but with more and more complex tasks, we can close that loop, and the AI can learn how to control the network, and this gives you this adaptive network. All right, so that's the stage and the context for my talk. Maybe just now double clicking a little bit. A cartoon view of telecom networks and their operations is shown here. So at the bottom, you have your network. And the network, it has an optical technology, like maybe for long distance, kind of the highways of the network. And on top of the optical network, you have an IP network. And here too, you have this, if you like, the big boulevards or even highways at the IP layer. But then you do with, as you get closer to the homes and the buildings, right, you have your access network. Anyway, this is a huge, and eventually your cell phone towers and all that. So it's a huge, complicated multi-vendor network. And this network is producing, as I already mentioned, a bunch of performance monitoring data, also a fair bit of alarms or events, things that happen this is all, streamed to a team of people that we call NOC. So NOC is the Network Operations Center. You can imagine a room filled with computer screens, TV screens, people watching them and making sure the network is up and running 24/7. Now, sometimes there are issues in the network for, variety of reasons, really. So when something happens that needs, that is actually an operational problem, and then the team of people here, they will open a ticket, they will follow up. So they observe basically some alarms, some patterns from the data that they know because they're experts. They open a ticket, they follow up, and then they go and they fix something. They change the network configuration, they provision something else. So they take a remedial action to resolve the issue. So now for machine, that this is all working today. However, it requires can AI help with the answer is yes. This is precisely what we're working on. So you use the AI. The input features of our AI models are these alarms and performance monitoring metrics from the network, and potentially also the tickets. Tickets can be either input features or they can be labels if you think in terms of supervised learning. And then there are the remedial actions here. These two can be labels for when to act, what actions were taken in what circumstances. But also in terms of reinforcement learning, right? This raw data is giving you the network state. And the remedial actions, are obviously the actions that you can take in RL. And then instead of labels, you can have these domain experts here, basically the design a reward function, which is capturing what they want to maximize when they do their job. Okay. So this is how we we apply RL for telecom networking and closed loop network operations. Now, when I said in my title superhuman, so I mean, personally, I think superhuman performance is the most exciting aspect of AI. AI applications to me are largely about automation, so you can automate things that humans can do. But instead of having an army of people doing something repetitively, you can have the computer do it for you. But in some cases, the AI can do even better than the humans. There's a limited number of tasks at which AI has achieved that today, but this list is growing every year, I suppose. So there are two ways to do that. Maybe you guys know this very well. On the left, you can use supervised machine learning, which is basically learning from examples. Very successful for computer vision, natural language processing, and others. Also in networking, we use this extensively. So, computers in general, they can do the same thing over and over. They can crunch more data than humans. So if you show so many pictures to a computer and you tell it what it is and you do it again and again and again, it becomes better than human at recognizing these pictures of cats and tables and cars and whatnot, like at the bottom. But and we do use again this technique. But another technique is reinforcement learning. This is learning by trial and error. This one very impressive and very famous example of RL success is, of course, in games, board games like the game of Go and this AlphaGo Zero, right? You have the two computers playing Go against each other for 1 million games. After a while, they become pretty damn good and much better than humans. So that is impressive. But you can also, with RL, now computers also become better than humans at video games. RL is important, but the board games are cool for academic research, but they are they are somewhat useful, but they are not exactly applicable to our problem, the telecom networks. What is more close to our problems is self-driving cars, in the sense that a self-driving car, you can never crash the car. You want to leverage the power of RL as a technique, but you never want to crash a car. Unlike a video game, you can be game over 10,000 times. It doesn't matter. You learn each time and you become better and better. But for us, we don't want to crash. But that can be done. And again, I'll talk about it towards the end. So we get our inspiration from self-driving cars to design self-driving telecom networks. And now I want to advertise one recent paper that I did with my collaborators from Ottawa U. So where we claim, maybe for the first, so I mentioned, right, there's a growing list of tasks at which you can achieve superhuman performance. And in our lab, we think we have demonstrated for the first time superhuman performance for closed loop network operations. So this is hopefully coming soon in IEEE Network Magazine, so stay tuned. But anyway, I'll give you the punches in the next slides. So here's the prototype that we've documented in that paper. So it goes like this. At the core of it, there is this software software application that we call Action Recommendation Engine. A recommendation engine can be something that Netflix or Amazon uses to recommend for you what movie you might like or what else you might want to purchase. But for us, we use it as if we put ourselves in the shoes of a network operator, and we given the network state, we recommend you may want to take this or that action to fix a problem or optimize your network operations. So now in our lab, we mimic indeed kind of people watching Netflix, if you want, or other videos from anywhere, really. So, and these are these people here on the left. These are all video players, and they want to consume video streams that are hosted right there on the right on the other side. So for the content to reach the end users, it needs to go through an IP network. A toy network, okay, it's not a production network, it's a small network with 5 routers. But here the idea is the network, first it has to be real, so it is real traffic, real videos. Also, we're mixing this with file transfers like secure FTP. And yeah, the network has to be simple enough that we can solve the problem in a year with good PhD students. But at the same time, it's not trivial that you could have guessed anyway the optimal solution from the beginning, and it's basically not it's a real problem where the optimal solution is not obvious. So we have so here for the videos to reach the end users, right? There are 3 possible paths. You can see here the path 1, the path 2, and the path 3. And now we put ourselves in the shoes of an operator of this AS number 1. So AS in BGP networking, this is for autonomous system, but it basically means one network operator. They are in charge of this part of the network, and so they control the path 1 and path 2. They can also outsource traffic on path 3, but then it costs more. So basically, we are aware of the OPEX. We're putting ourselves in the shoes of the operator. We want to minimize the cost of operating that network. We want to take the shortest path as much as we can and use our own bandwidth as much as we can, not borrow from third party. But at the same time, we also want to give the best possible quality of experience to our end users. And so these are the video players here. The good thing with video players is we can measure the actual quality of experience from the videos that are playing. So we play real movies and we literally measure the quality of experience of the video players. So we want to maximize QoE, quality of experience, while minimizing OPEX for the network operator. So that's actually our reward function, QoE minus OPEX for the RL. And yeah, because now this is in the lab, so we purposely break things in the network once in a while, and we have tuned also this, and we change the demand for movies over time. It's not constant. Sometimes there are peaks, sometimes it's very quiet, and then sometimes there are congestion. There is congestion if everybody tries to use the same shortest path, and so on. So now, how do we map this to our simplified view of the network operations here? Well, we just described in fair amount of details the network at the bottom. And now this network is, I spoke about telemetry, right? So we observe we monitor that network with 66 metrics. Basically performance monitoring of every router, also the quality of service, end-to-end quality of service for the 3 paths. So this is stuff like latency, jitter, drop packets, throughput. And as I mentioned, the quality of experience of the end users, the video players. Now there are issues, as I said, and then there are 12 possible remedial actions to fix these issues. So it's basically rerouting some of the flows to take another path, or rebooting some of the router interfaces, or just wait and do nothing. Because by design, all the problems we introduce in the lab, they last for a while, but they are transient in nature, and they eventually disappear by themselves. So sometimes it's better to just wait. Because in terms of cost, if you send somebody to fix the problem, it also costs you something. I forgot to tell that. So I'm almost done. The only last thing that I have not yet described is the NOC itself. So, and this is the next slide. We don't have the luxury of having an actual NOC in our lab. So what we do is we mimic NOC with these 5 expert rules. They are common sense rules. They are rules of thumb. If you read them, you will see they make sense approximately. So basically, if you have congestion, as much as you are, again, you're in control of AS number 1. So if you see congestion in your network, you try to reroute to another route to where there's less traffic. Or if you see a router issue, well, you may, and you could not fix the problem with just rerouting, you can reboot the router. You try to, and so on. Now, 2 questions here. One is, can an AI learn these rules without us programming these rules at all, just from these metrics and these actions as, either labels or anyway as data that we feed to the AI? Can we learn these rules? And also, especially if we use RL, are these rules actually optimal, or can the AI learn an even better set of rules? So these are our research questions. So about the first question, the simplest answer for that is learn the rules, these rules specifically, not invent new ones, just learn these ones. This is better suited for a supervised machine learning problem. So I don't provide too much details, for this stuff, but I point to a paper that will be published soon at the bottom of the page, about this. But here's the result. Bottom line is the x-axis here is time, and the y-axis is this quality of experience minus OPEX. Sorry, it's not revenue. Should really fix that. The slide is the 3rd time I think I show it with the mistake. But yeah, you follow me, I think. So we want to maximize the y-axis. And so, yeah, as time passes and as our network lab runs by itself, as I explained, and these rules are executed automatically as a closed loop system. Well, actually, if we don't execute these rules automatically, we just let the transient problems happen, do what they have to do, cause some damage in the network, but then disappear eventually. We get the black curve. So first of all, you can see that the network, even if you just let it run on its own, it would still survive. It's above 0 most of the time, and yeah. However, if you now execute in blue the expert rules, then you get a much better QoE minus OPEX. And then the exciting part is the green curve, which is, we let the system run for a while using the historical data set. We train the supervised machine learning, and then we take the model that we train, we put it inside the closed loop. Instead of executing the rules, we just execute the predictions from the supervised ML, what would NOC have done in this case. And we execute that, and we get the blue curve. So works. We reproduce the NOC logic with our supervised ML model. Now, that's great. Already, it's huge. We can automate, can help NOC operations a lot with this already. Technique or technology. So here you see the same graph. The y-axis here, at least you look at this red and orange curve. So the y-axis is QoE minus OPEX metric, and the x-axis here is time. This is kind of zooming on first 200 steps, and you see that the rules, expert rules, and the RL agent perform the same for a while, but at some point some situation happens where actually the RL found a better solution than the expert rules, and then overall it performs better. So yes, while the supervised learning was simply copying the knock actions and automating them, but still just copying. With RL now, we through the reward function, we evaluate the effectiveness of the actions, and we can actually not only reproduce the common sense rules, but discover new ones. If I, instead of this abstracted result, QoE minus OPEX, I can also show more concrete results from this for the same 200 steps here. Here you see the actions, some of the actions that can be taken as part of the closed loop. So this is according to the expert rules. You see what actions the system took over time. But after training with RL, you see that it managed to run the network in more stably. It learned that some of these actions are not actually necessary. You can run your network smoother, take less action, and so minimize your OPEX for the same QoE. So that's great. In fact, it's not even the same QoE. You can, and this is the next slide, you actually can get better QoE sometimes with RL compared to expert rules. And so here you can see the here knock expert rules versus RL at the bottom for the same situation. And what you see here is the video buffer size. So a higher video buffer is better in terms of QoE. When it gets too low, it means basically when you watch a movie, there's some spinning wheel. You need your buffer is empty. You need to download more streams, and that's annoying. So here we don't want that, and it happened here for the end users that happen to be on path 2. But for RL, it's very smooth, very stable, much less issues. Also, if you notice, the RL kind of learned that it's actually better. The end users are show up on any of the 3 paths randomly at first, but it basically just exploiting the path 1 as much as it can. That's the bottom line that what was learned here. But yeah, so that's that gives these superhuman results at this point, better than the expert rules. So that's great, but that's a lab prototype. Now, if we wanted to, and that's the last topic I want to bring up. Now, yeah, that's great, but how can we now bring this to a production network that needs to be operating 24/7, cannot afford trial and error in the early phase where you can, some of the trials can actually be, very silly things. So we don't want that. That's fine. So there are actually 2 solutions that you can even combine, but so 2 methods. The first method, maybe the most well-known, is with a simulator plus transfer learning. So you train on a fast simulator, then you transfer to the real network, and to the extent that your simulator is realistic enough, and then the transfer learning to the real network will be successful. This is actually the case for our lab prototype. So here it is kind of 3-step with method 1, right? So you see at first in the fast simulator only, we were basically, here we use actor critics, A to C. Well, we also tried other methods, WQ learning and others. This is where Sadi was shining here. But yeah, try basically as usual with machine learning, a whole bunch of hyperparameters and see how well you're learning in each case and so on. So you do this type of exploration with the fast simulator. Also, you can fast forward the reality with a simulator. So it's actually a good idea to do that. And then step 2, once you know approximately what you want to, where you want to be in the hyperparameter space, then you can actually, do the final optimization of your RL training with, either a more complete simulator and or with, more stats. So you push your RL training and you benchmark the results as best as you can. And so here you can see this is still with the simulator, but if you let it run for many more steps, you see that in blue, the RL consistently outperformed the expert rules. So we're satisfied with this. Then the next and last step is the transfer learning. So now we take that exact model, pre-trained with the simulator, and we deploy it now in production in the real network. And this curve that I already showed you, this graph wasn't exactly like that. This is just at the beginning, the model's already trained, but it was trained, it's this model here, it was trained with the simulator. Now transfer learning works in this case. And then there you go. You have your RL model on the real network. That, of course, has the assumption that you do have a simulator that is realistic enough for your real network. But if you don't have that, or anyway, in addition to that or complementary to that, you have another method that you can use, method 2, where you have no simulator at all. Everything is done only with the real network. But here you leverage the offline pre-training, because we often think of RL as something that's done live, learn by trial and error live on the fly, but that's not, you can do that, of course, but that's not the only thing you can do. You can also do batch offline training of RL. And in this case, as you all know, in RL, one of the key hyperparameter is exploitation versus exploration. So you can think of it as the batch pre-training is basically you have zero exploration. You don't let the RL agent decide on the actions, but you just look in the historical data, whatever actions were taken in this case by NOC. Well, this is the action that was taken, just like if the RL agent had decided to take the action, but it's not. It was taken by NOC, but doesn't matter. You see the state of the network, you see what action was taken, and then you also see what reward you get when this action was taken in this state. And so by doing this over and over from historical data, you can pre-train your RL, and you can learn, your reward. Through you can learn to model the network like this. And so then here, what we have done with our prototype is we pre-train like this with historical data, and then for the first part with the dashed lines here, we deploy still on the same real network from which it was pre-trained offline. Now we deploy it online, but at first we put exploration to 0. So then the RL will not try anything new that was never seen before. It will, if everything goes well, it will just reproduce what was done historically. So it's almost like supervised learning at this stage. And then if this is convincing, you see that the operations are like you expect, then what you can do is you can put safeguards around your closed loop RL and so on, and gradually allow for some exploration on the production network. And then if you do that, you see that maybe more slowly than with an aggressive training on the simulator, but still eventually the RL will learn these newer, better strategies with this prudent exploration in this way. Okay, so I'm done with this. Now just the last slide, the conclusion. So first of all, I repeat this adaptive network vision, and with the little icon on the top right. And in this icon, AI is instrumental for Ciena's adaptive network vision. Today, I presented one of the most cutting edge prototype we have using RL to close these loops. But I want to point out that we also have several machine learning applications already in production today that I did not talk too much about, but yeah, that do a great job and that we are very excited about. And yes, in terms of, so that's in production. Then in terms of research, well, in terms of AI research in the space of telecommunications network, I think Ciena, we are at the cutting edge in this domain of AI applications. And so I'm very proud of that. And now with several other collaborators in Ciena working on this by now. And we have also very fruitful collaborations with Canadian universities, notably for this forum here. So like such as Ottawa U, that was instrumental for these results presented today. And yeah, finally, we have this action recommendation engine prototype, which has demonstrated feasibility of superhuman network operations right now presently in the lab, but we are actively working with partners to test this in the field as well and eventually get to production networks with our customers.
Is it possible for this kind of problem to be solved with traditional optimization techniques like linear programming?
Yes, I'm sure it's possible. Well, okay, the thing with closing loops in telecom networks. So, okay, so I think as far as I know about linear programming, you can optimize you need to define the function, the heuristic function that you wish to optimize, and then you can optimize it. But you can use these techniques, I believe, but especially if you have a multi-vendor network, it depends what it is, but if it's a multi-vendor telecom network, it becomes quite complicated, and no single person is an expert about every component of that network, right? So it becomes kind of difficult. So defining the heuristic function that you then would like to optimize from first principles, if you like, from domain expertise, is quite difficult. It's not impossible, I suppose, but historically it has not been very successful. There is not so many automated closed loop in telecom networks today, I think mainly because of that. It quickly becomes too complicated. So, but still, that knowledge of how the network works exists. It's a collective team of people that have it. Everybody knows about their parts. So you need to collect data from the whole team. Then you can have maybe an AI learn from it. So that's why I prefer that approach. But yeah, if you can define a heuristic function, then you can use linear programming to optimize it. Absolutely.